This is lecture 51, and it is on the twin paradox. This is a popular topic. People like to talk about it because I guess people are interested in, weird stuff and, time travel. I was actually, in this lecture, I will be demonstrating time travel. On your mark, get set, go. I've just traveled 5 seconds into the future. We were always traveling in time, right? So, but, and unfortunately there's no known way to travel back in time, but there is a kind of a way to travel forward in time if by what you mean is that you're going to get in some machine and when you get out, everyone else will be older, it'll be a later time, and you'll be approximately the same age or very nearly the same age. And the twin paradox is kind of an illustration of that. Okay, and so let's take a look at it. Let's set it up first. We're gonna use our velocity to be 80% the speed of light, which comes out to be in our normalized units where we let the speed of light be equal to 1. Conveniently, this will be represented by the ratio 4/5. Okay, which means that gamma is going to be 5/3. It's a handy one. Another handy one to use if you want to have much higher velocity, I think is 96% the speed of light. I think the velocity is 24/25. I'm not sure what gamma would be. You have to plug it in and see. But yeah, this is a handy one if you want easy numbers to work with, which is what we would like in this case. So these are our velocities. So what is it that's moving? So we're going to describe a system in which I'm going to make Earth a little bit bigger. Let's make it about like this, and then we're going to have a guy, well maybe we'll write a rocket ship, that would probably be a better description, right? There's our rocket ship, okay, and it's going to travel to a distant planet whose distance in the Earth frame is 20 light years, okay? So I guess I'll just draw a big line and say this is L equals 20 light years, Ly for light years. All right, so what do we, and also when we start out, this guy will have a clock which says 0 years, and this guy will have a clock which also says 0 years. So they synchronize in the usual fashion, right, at the origin, at the axis origins, right? Okay, so at some point later in time, I'm going to draw the Earth here. I'll redraw the planet over here. At some point, our rocket ship will arrive. And the question, of course, what does the clock say? Let me add one thing before I move on to that. We're going to synchronize the clocks on Earth and on this planet. And how will we do that? Well, you can imagine going halfway between the two and putting up a little light emitter that emits a light signal at some point, and when the two light waves arrive at the two planets, they agree to start their clocks and say 0 years, okay? And you might recall that if the distances are the same, and since light is a constant, we can thereby synchronize these two clocks so that here on this planet, we also have 0 years, okay? All right. Now, how much time has elapsed back on Earth, and consequently on this planet, from the Earth frame? We would say, okay, well, the rocket ship was traveling at 4/5 the speed of light, right? And so what is the time that it took for it to get there? Well, it had to travel 20 light years, right? So remember that velocity times time equals distance, right? Yeah. And so if I simply take the distance and divide it by the velocity, that should give me the time, right? So I can take 20 and I can divide it by the velocity, which is 4/5, which is the same thing as multiplying times 5/4, right? You can see this will give me 25. So 25 years is what the clock on this planet says, and on this planet. 25 years, right?
Yeah.
Got that?
Yeah.
Okay. I just realized I shouldn't have drawn this so big because I'm going to need to draw another set of pictures. That's okay. So it took 25 years. Now the reason this clock also says 25 years is because remember they're synchronized. Okay? Since they're synchronized, whatever this clock says, this clock will say too. because in this stationary frame, all the clocks are synchronized. Now, what about the rocket ship? Well, there's a couple of ways you can look at this. We can say, well, we can use time dilation, right? We can say, well, the delta t, we know that 25 years, right, which is what we saw, will be equal to gamma times whatever the time is it took for them, delta t prime. Okay? And if we solve for delta t prime, since gamma is 5/3, this would say that delta t prime equals 25 times 3 over 5, which is going to give me 15. Right? So 15 years. So, as you might expect, the observers on Earth, and remember, the observers on Earth, everybody in this frame is in the Earth frame. We've got graduate students standing at every point in space throughout here holding a clock. They know what position they're at, so they're recording things that they see. And it's this graduate student holding the clock here on this planet that observed that the ship arrived and that can mark the end of the journey being 25 years. Okay? Because his clock says, hey, it's 25 years later, I see the spaceship arrive. And then later they all get together and they look at the books and they say, oh, for 25 years, spaceship arrives. Okay? There are no light signals going back. You don't have to account for light signals traveling back and forth, sending communication messages or anything like that. Okay. So that's where we are with this. Now, maybe I'm going to make some... so what did we find? We found that delta t was equal to 25 years, and that delta t prime was equal to 15 years. These are our observations here. All right, now I want to change it up, and I want to look at things from the perspective of the rocket ship. Okay? Oh, first I was going to show you, there's another way you can calculate this, right? I can calculate t prime directly from the Lorentz transformation, and this is how it would look. I would write that t prime is equal to gamma times L over v, that's the time, right? It's the distance L divided by the velocity, right, that the spaceship is traveling at. That's the time part. Minus the Vx part will be V times X, which is just L, right? And if I plug in the numbers for this, gamma is 5/3. L over V, we already know what that's going to come out to be, right? That's going to be 15 minus V times L. That's 4/5 times L is 20, right? That's going to give me, that's going to kind of give me 16 there. Oh, did I mess something up? No, not 15. That's 25. L divided by V, that's 20 divided by, or times 5/4, that's 25. 25, right? And so that gives me 5/3 times 25 minus 16 is 9. The 3's cancel. Gives me 15 years, right? So I can calculate it directly from the Lorentz transformation if I'd like. Or I can just say, well, we see time dilation, right? And use the gamma factor. All right. So that is from the Earth frame perspective. What does the rocket see? I'm going to draw it a little bit differently from the rocket, if you don't mind. Put the rocket right here. Here's the Earth. Here's the planet. And there's actually a reason it looks closer together, okay? Because remember, in this rocket, which is moving at velocity v, but I'm not going to write that. What I want to write is that the Earth and the planet, from the rocket's perspective, is moving at minus v, okay? So when it begins the journey, it will agree. They will still synchronize their clocks. This will be 0 years, right? And then sometime later, what's going to happen? Well, the rocket doesn't move because you're in the rocket. That's the stationary frame now, right? It's the Earth and the planets that are moving, right? So this distant planet is racing towards you at negative 4/5 v, at negative 80% the speed of light. It's going in that direction now, right? Yeah. So what does it look like when it finally arrives at you? Well, you're in the same position as before. Now here's the planet, and Earth, of course, will be back here somewhere, right?
Yeah.
Yes? How much time has evolved for the rocket? Well, what is the distance for the rocket? It's a little bit different than L, right? Remember, L was 20 light years. But L prime, right, it's going to be length contracted because this is a moving frame, right? It's moving with minus v. And so it's going to experience a length contraction. This distance here, L prime, is equal to L divided by gamma, which is, well, L is 20, gamma is 5/3, so that's 20 times 3/5. It's going to be 12. Right?
Yeah.
I think that's right. 12 light years is this distance, right? So how long did it take the Earth planet system to travel that distance? Well, it's going to be the distance divided by the velocity. So the delta t prime that you experience, right, is the 12 light years divided by the velocity, which is the same thing as multiplying times 5 over 4, and that equals equal to 15 years. Okay? So the rocket ship sees 15 years. I guess I wrote YR for years. Okay?
Okay.
Now we could have computed it directly from the Lorentz transformation, right? It's a little trickier because we have the negative velocities. Also, I'm going to keep the prime. I'm going to keep calling the rocket ship the prime frame, so you won't be able to just look at the equations that we put up before for the Lorentz transformations and directly map them, because now the primes will be the unprimed frames, right? But it looks like this nonetheless. We'll say that the time t, that is the time in the Earth frame, right, will be equal to gamma times t prime. I'll write this down first. Minus the velocity is negative, so it'll be minus the negative velocity plus the velocity times x prime, right? So what are the values that go in here? Well, t prime, we've already stated, is 15 years, right? Actually, let's put it in with the actual values. This was L prime over V minus, plus V times L prime. X prime will be a negative value, right? Because it's shifted to the left a distance L prime. So this makes this, again, minus VL prime. I think that is all correct. And that will give us 5 over 3 times 12 times 5/4 minus 4/5 times 12. And that is going to factor out the 12. It's going to be 9. Okay? And you can try the math on your own. It's just adding and subtracting fractions, but it should be 9. So we have 9 years. Now, jump out of our rocket ship and land on this planet. We see that this would also be at 9 years. So what's the catch here, right? How can we have? So what do we get in this case? Now we get that delta t prime was 15 years, but delta t is just 9 years. Question mark. So this is the paradox part, right? How can that be? So what's the paradox? Well, that's the paradox, right? We agree upon the time on the spaceship, but we disagree on the time on the two planets, or on the planet, right? So when we look at it from the Earth frame, we see the rocket ship arriving at the planet when the planet says 25 years. But from the rocket ship perspective, we see it landing on the planet when the planet says 9 years, okay?
Okay.
So this is the paradox, right? And this just stems from the fact that both parties, right, both the rocket ship frame and the Earth frame, see relative motion, and so they see time dilation. They both observe the other frame having slow time during the trip, okay? So both of them would think if they were to make the journey back, it would be exactly the same thing, just double the times up and the distances, and they would see that they would expect their twin to have aged less, right? The guy on the rocket would say, well, my twin is younger because of time dilation. And the guy on Earth would say, my twin is younger because of time dilation. So we have to resolve this paradox and figure out if either of them are younger or if they're exactly the same age, okay?
Okay.
So what's the problem here? How do we resolve it, rather? Let me show you how to resolve it. I guess I could have kept that picture, and I actually want to keep that picture around. I'm going to think about it a little bit differently, though, okay? So we know we had a rocket ship. We had 15 years for his time, and this said 9. I'm going to leave it blank here, okay? Let's go back to the start of the journey, and let's think about this rocket ship. Instead of it being a rocket ship, let's think of it as a moving sidewalk. Have you ever been to an airport and seen those moving sidewalks? Right? If you want to, make a quick trip from one terminal to another, and you're in a hurry to make your plane or whatever, you get on this moving sidewalk and it'll jet you along at a higher speed, right? So let's imagine there was this moving sidewalk, right, all the way, well, from minus infinity to positive infinity. And then what we're doing is that when we start out, we're here on Earth, right? And, of course, in this case, we see the same thing that the Earth frame sees. We see both of these clocks synchronized, right? So this is 0 years, and this says 0 years, and then in an instant, I jump up onto this moving sidewalk, okay?
All right.
Well, the moving sidewalk is a different frame of reference. So let's consider what that moving sidewalk sees real quickly, okay? We can agree to synchronize once he's on board. We can agree that he can make his clock say 0 years just as he passes the Earth, okay? So that 0 years are in agreement. But if you remember, the relativity of simultaneity, right, says that clocks and moving reference frames are not synchronized, okay? You remember that from last time? So this may be at 0 years, but this will not be, okay? Because from the perspective of the reference frame of the moving sidewalk, these planets are moving. At t equals 0, or well, just before t equals 0, sometime earlier, this light flash took off, right? And it was shining in both directions at the same speed, right? And whenever it arrived at the two planets, the planets would click their timers and they would say, time is 0 years, right?
Yeah.
Well, what do you know, right, if you were to like imagine, just for a moment, this kind of the light waves going out, right, over time. They look like this, right? So this is starting and then later in time. And maybe initially you started out the distance was the same, but if the planets are moving in this direction, right, then you can see that, I probably made them move too far. Now they're faster than the speed of light, aren't they? Let's say that here's the time when the signal arrives at Earth, but this signal, right, obviously already arrived and has already passed this planet. So this planet's clock timer has been going for some time before Earth starts its timer. Okay? And how do we calculate that number? Well, you might recall the formula was delta t sub s. That's the synchronization disparity. I don't know. There's no real term for it, but it's equal to v times L, the distance to the planet, divided by c squared. But c squared for us is 1. Okay? And there's a gamma in here. Sorry, and a gamma factor. Right? So what is that for us? Well, gamma is 5/3, v is 4/5, and L is it L or L prime? I think it's L, right? Well, let's try it with, I think this should be L prime actually, since we're in the moving sidewalk system. And L prime was 12, right? So let's see what these numbers give us. The 5s will cancel. The 3 will cancel there. I get 4 times 4 equals 16, yes. So it was L prime. So from the sidewalk's point of view, here, right, it's not 0 years that this planet is at. It's at 16 years already. It's been ticking for 16 years, right, because the light signal arrived very quickly because it was rushing towards the light signal, right, whereas the Earth was racing away from the light signal, so it took longer for the light to get to it, okay? So this clock started up 16 years before Earth's clock started up. So when we begin our journey, this clock is at 16 years, this clock is at 0, okay? Now remember that delta t from the Earth frame was 25 years, right?
Yeah.
And we found 9 years, right? So if you think in your head, well, 16 plus 9, what does that equal to?
25.
25, right? So in this system, when I arrived, erase these pictures because they're distracting, I think. When I arrived, 9 years has elapsed from my perspective on the moving sidewalk. Yes, I'm sorry that I drew a rock. I meant to draw another moving sidewalk, but that's fine. But you have to add to it the start time of this clock, 16 years, right? 25. Okay?
Okay.
Now, if I were to jump off of that sidewalk onto this planet, then immediately these two would be in agreement, okay? And they would both say 25 years. But what if I'm just zipping by and I'm still on the moving sidewalk? As I pass, I'll see this read 25 years, but this Earth time will just be 9 still. Why is it 9? Well, because initially it was 0. So I take 9 plus 0 is still 9, you see? Whereas here I took, the delta t was 9 years, plus the start time of 16, not 0, right? So this one reads 25, okay? So if I reverse course, I come back, right? Everything is just, take these numbers and double them, right? So the one-way trip to the planet, right? My twin back on Earth had aged 25 years. I had aged 9. If I turned around immediately and came back, right, then it would look like I would age 18 years and my twin would age 50. Okay?
Okay.
And it's a real effect. People, they haven't sent twins into space or anything like that, but they put clocks, very high-precision clocks on fast-moving aircraft, I think, and have observed exactly this. Let's look at it from another perspective that may or may not give any insight into it. Again, special relativity is not intuitive because it's not part of our everyday reality, so it's not, the forces of evolution have not given us the intuition to, really grasp it easily. So let's draw a space-time diagram of this, okay? And in this case, I'll put the full trip, right? The journey there and the return trip back. So here's t. This is the Earth planet frame, okay? We'll make this distance here be L. That's the 20 light years, okay? Does that look good? It's pretty good. I think that's close enough, okay? So, this is the trip to the planet, right? The world line. I'm assuming I'm traveling at a constant velocity. And then I immediately turn around and I come back, right? So, this is the t prime axes, right? The world lines of the spaceship or the guy on the moving sidewalk, right? And I want to draw a line. Remember his x-axis, right? If you remember where our light line is, the x-axis will be like this, and so we need things that are always parallel to that, right? So if I draw a line of simultaneity, right? That is a line where I'm going to kind of extend this out so I can get this line. We have the light line here, and then my x prime axis would look like this. Okay? So this is x prime axis at the time when it arrives at the planet. Okay? When I reverse direction, right, now I'm going to draw another line of simultaneity in that direction, and it's going to look like this. Okay? So this bit of time that I observe my twin brother aging, right, during the journey to the planet, right, is represented by this little bit of time here, right? And then coming back, when I turn around, I see him aging this little bit of time here. Now you're wondering, what is this gap in the middle, right? Well, this is the relativity of simultaneity. This is that 16 years that we had found before, right? So I guess it's 32 years for the round trip, right? So we have 9 years here, right? Yeah, I think that's right. So we've got the 32 years, that's just 16 times 2. And then we've got 18, right? We get the 50 years that he's aged, right?
Yes.
You understand that?
Yeah.
9 years. I'll just write in 9 years. This distance here is, I'll write like this, 32 years. And then we've got another 9 years, okay? So the weird thing is that whenever I turned around, right, when I reverse direction, I see my brother only aged 9 years, and I've aged 15, right? I'm like, well, God, my brother's younger than I am. How crazy is that? And then I turn around, right, and in that instant, for whatever reason, right, my brother appears to be 32 years older now. Okay?
Okay.
And then I travel back, right, and he ages another 9 years. The total, 9 plus 32 plus 9, 50 years he's aged. Me, I've aged 15 years going this way, 15 years going that way. Okay?
All right.
I'm 30 years older, my brother is 50 years older. So I've traveled in time, in a sense, that when I return to my planet is older than I am, right? And so that's kind of, what traveling in time is about, at least if you travel to the future. Right? So can't do it to the past, but you can travel to the future. So if I went really, really fast, I could make these numbers much, much bigger. And you could easily find some speed that you could travel, in which you could travel as far into the future as you wanted without aging very much at all. It would be a huge speed, and I don't know how you'd ever get to that speed, but yeah, you could do it, I suppose. Any questions at this point? And it should make sense, right? It's not intuitive. There's no like, oh, it's because of, he was wearing the right sandals, or yeah, it's not anything like that. So what is it that's different about the two reference frames, by the way, right?
Yeah.
And this is one of these things that the internet trolls love to fiercely debate, and the non-physicists, like armchair physicists, like to speculate upon, and that is, what is the origin of this? And but I think the answer is pretty simple. I think it's, if you look at the two reference frames, what's different about them? Well, imagine you're the twin that stayed on Earth.
Yeah.
Okay.
Okay.
And then your other twin, who jumped on the moving sidewalk? The other twin, right?
Yeah.
So, yeah. Now, is it purely because there was acceleration? No, that's not the case. I mean, I could easily, have the Earth frame do a little acceleration of equal magnitude right here. It would change the numbers a little bit, but not by much. It's because you've accelerated onto this moving reference frame where this relativity of simultaneity effect took place. Okay?
All right.
Yeah, I mean, this gap is bigger the faster you go, okay? If you go faster, this gap opens up really, really wide, okay? Because my lines of simultaneity, are really close to the same as the speed of light. It's very vertical, right? So, yeah, it's a velocity-dependent effect, okay? So it's not necessary. It's not that you have to like use general relativity, which is what you normally use to talk about acceleration, to figure out what's happening. It's really just this relativity of simultaneity issue, this clock synchronization business. Whether there's some deeper metaphysical meaning to it, I don't know. I mean, it's not really what physicists do. Could be, but who cares? You never measure it anyways. This you can measure, and the numbers work exactly as we should, calculate them. So in that sense, we understand it and that we can calculate it. What does it mean? What does anything mean? Okay, so that's all I have to say about that. And next time, what we'll talk about is a little lighter, easier material in a sense, a little more math. But when we started, we talked about Galilean relativity, and one of the results that we showed was that if I'm on a train and I throw a ball with a speed that call it u on the train, then to see what the speed of the ball is relative to the ground, I would just simply add the speed of the train plus the speed of the ball, right? Yeah. So what does that look like in special relativity? And so we'll look at that briefly next time.